Hi there, good morning, good afternoon, or good evening, wherever you are. This is Ali Ouni from ETS Montreal. I'm glad to present this tutorial today on search-based software engineering with Professor Mohamed Ouam Kaur from Rochester Institute of Technology. This tutorial is part of the Genetic and Evolutionary Computation Conference, GECCO 2021, being virtual this year.
Thank you, Ali. This is Mohammed speaking. So in this tutorial, me and Ali will walk you through the challenges, opportunities, and recent applications of the search-based software engineering.
So first of all, we would like to thank Professors Mark Harman and Marwan Kasantini for the inspiration to prepare this tutorial.
We also would like to thank our students, co-authors, and collaborators for helping with preparation of the materials of this tutorial.
So this tutorial will be presented by myself, Ali Ouni. I'm Associate Professor at the Department of Software Engineering and IT at ETS Montreal, which is part of the University of Quebec. I received my PhD in 2015 and I'm working mainly on the application of search-based techniques or optimization techniques to solve problems in software engineering, including software refactoring, software maintenance and evolution, and other problems related to software quality.
So I'm also assistant professor at the Department of Software Engineering at RIT and have received my PhD in 2016 from the University of Michigan Dearborn. And also my research interest includes tackling software engineering problems using alt-digit algorithms and evolutionary algorithms. So today's agenda will cover various aspects. First of all, we'll talk about the differences between software engineering and science in general, or science and engineering in general. Then we will go deeper into the definition of search-based software engineering. Then we will look at some recent applications of search-based software engineering into multiple software engineering problems, including performance regression, code review, etc. Then we will have some demonstration of how we can take a software engineering problem and then develop a potential search-based or search algorithm that can solve that problem, and we'll also show how this can be sort of a hands-on experience for whoever wants to try this. And then we will conclude with looking at the challenges and future work in search-based software engineering. So to start with, we can look at the difference between science and engineering. So science is about using experimentation and analysis to explore the world around us. We take a problem, we characterize it, we quantify, and then we model it. This is sort of the role of what scientists would be doing. On the other side, in engineering, we take that information from the scientists, and then we look at and we try to design and develop products that are going to allow to and improve the quality of human life. So engineering offers humanity hope because science gives us a set of information and engineering gives us the practical solution. So if you look deeply into science and what scientists ask questions about, you will see that they always look at the theory part of things. They will ask questions like how things are theoretically done, right? While engineers in general, they look at how things are practically done. So the scientist merely explores what exists, while the engineers create what has not existed before. Per analogy, a computer scientist will look at the fundamental principles behind computation and how it works, while software engineers, they will look at how to complete some specifications and meet designs and do some implementation testing within a set of constrained environment and a lot of limitations. So when you are solving a problem, would you consider yourself to be a scientist or a computer scientist or a software engineer? This is always a good question, and perhaps today we will see how the synergy between both computer scientists and software engineers can create that interesting and in relationship that will define what we call the search-based software engineering. And to dig deeper into the formal definition of search-based software engineering and how it was initially coined, My colleague Ali will start, will take this up, this part.
Okay, so thank you, Mohammed M. So before delving into the details of search-based software engineering, let us see what are the common words that engineers talk about all the time. So we checked from different engineering fields. Researchers and practitioners are mostly talking about optimize, analyze, solution, tolerance, and many other related aspects. So we see that they named here the word optimize twice in British and in American. So optimization is in the core of search-based software engineering. And so the term search-based software engineering was coined in 2001 by Mark Harman, and SBSE is about the use of intelligent search techniques to explore large search spaces. And this exploration is guided by what we call fitness function that captures the properties of desirable solutions that we would like to have to solve a given problem. And once a problem is formulated as a search-based software engineering problem, there are multiple algorithms that are ready-made that we can use to solve our problem, like genetic programming, hill climbing, harmony search, particle swarm optimization, simulated annealing, and many other algorithms that are ready for use. And these algorithms fall under the evolutionary search algorithms as part of machine learning, which are all under artificial intelligence algorithms to be used originally in robotics, and today is almost used in almost all fields today. So when we look at search-based software engineering, this is mainly an intersection between two fields, optimization and software engineering. And for each field, like in search-based optimization, there are multiple algorithms that are ready to use. So going from single objective algorithms like genetic algorithms or ant colony optimization, particle swarm optimization, to multi-objective optimization algorithms like NSJ2 and NSJ3 and many other algorithms. And today there are many objective algorithms that are ready to use. When we look also at the software engineering part, people from software engineering, they have many problems to be solved, like automated test generation, source code refactoring, software management, requirement engineering, fault localization, and many other problems that are by nature search problems or optimization problems. And then this intersection led to many subfields under search-based software engineering, like search-based testing, search-based refactoring, search-based software management, search-based program repair, and there are even some dedicated workshops and special tracks for some of these fields, right, like search-based testing with an established community. And now, to adapt search-based software engineering to a given problem, there are different elements that need to be defined in order to adapt the technique to the problem. We start first from software engineering problem like source code refactoring, which is a common problem, so that people are trying to find solutions to solve or to improve the quality of their code through sequences of refactoring. So the first step is to make the encoding or to define the encoding of a solution, which could be like presented as a vector or as a tree, binary string, permutation encoding, or many other possible encoding schema. Then once this encoding is defined, we need to define what we call fitness function, which will capture the desirable properties of the solution that we are trying to find. Then we need to apply genetic or change operators in order to refine and to evolve the solution towards the optimal solution that we would like to have. And today, SBSE is growing very fast over time, and we can see the trend of the search-based software engineering field until mid 2012. So there are more than 1,600 authors from nearly over 300 institutions spread over more than 40 countries. And this is actually a realistic scenario, and the philosophy behind search-based software engineering encouraged a lot of researchers and practitioners all over the world to use search-based software engineering in solving their problems. And actually this is but maybe the question now is why this is growing very fast, and why this is attracting a lot of people to work on SBSE. So the answer is that in like other fields, we have a valuable opportunity to check many possible directions or many possible solutions for a given problem, and then select the best one. So in physical engineering, this could be costly, as we need to try different solutions or do different experimentations. This could be possible actually in practice, but this is very costly. However, in software engineering, for example, to fix a bug, we can change the structure of a program and try to find different patches to find the best one. So there is almost no cost for this experiment. We only need to try multiple solutions, check the code again if the bug is fixed or not. So this makes software engineering more attractive to apply search-based techniques or optimization techniques to solve problems. And let us look at an example of a space rocket to better understand this concept. So the goal is to find the optimal structure that maximizes the compression and minimize the fuel consumption. So this is extremely costly to try it physically on the space. So people usually they use simulation, but there is a risk that simulation here do not or is not very similar to what happens in practice, which makes some assumptions should be made, and these assumptions could be wrong or could not be validated as expected. So in software engineering, this could be more practical. For example, we can use optimization to find optimal design that maximizes cohesion and minimize coupling. So this is possible. We can modify the code, we can see what happens, and then undo our changes. This is possible and is not costly, and feasible, practical, and realistic. So today we all use software applications in our everyday life, so either in our smartphones, in our computers, cars, TV, washing machines, metro, so almost everywhere we are surrounded by millions of software systems around us that are ready to use by millions of users. So the number of available software applications is increasing exponentially. So our software industry today have a lot of new emerging challenges that need to be solved, and they want reliable and efficient solutions that can provide them with optimal solutions to solve these problems. So to better understand these challenges, let us see or let us listen to software engineers and see what kind of things they would say. So software engineers, we can find people working on requirements, working on design, on management, on testing, on maintenance. And people from requirements, they will tell you we need that all our requirements implemented, and we need them to balance software development cost and software or customer satisfaction. Also, people from design, they would say we need increased cohesion and decreased coupling. We want to have high modularity of our system. People also from management, they would say we need to reduce the risk while maintaining the completion time. And also people from testing, they would like to have very fewer tests that can find all the bugs in their system. And lastly, people from the maintenance, they would like to have optimizing all the metrics in their code, and which is sometimes very challenging as some metrics are conflicting. So all these problems have been addressed in the search-based software engineering literature with many publications over the last 2 decades. And so this is like search-based software engineering actually brings a lot of advantages. So first, SBSE is scalable. it provides scalable solutions are independently on the size of a system and also in an acceptable execution time. Also, SBSC is realistic as we can fix our objectives in advance to find solutions that fit our preferences and that can achieve or fit with our objectives that are predefined. Also, search-based software engineering is robust, provides robust solutions, and it works even in noisy environments. It also provides generic solutions, as our solution is not for a particular system, but it should work in multiple software systems that have the same problem. And finally, it provides also unification. So the same problem encoding could be applied to different problem instances like permutation problems, ordering problems, selection problems, etc. And using SBSE in the last few years, we have explored several applications of SBSE in different to solve different problems in software engineering, starting from automated refactoring recommendation to code smells detection to refactoring of web services, code review recommendation, down to continuous integration and software library use. Even we used recently these techniques in order to detect social issues or social debt in software projects. And in all these problems, we used search-based software engineering. So in the next, my colleague Mohamed Ouem, he will be presenting some of our recent applications to search-based software engineering, starting by performance regression using SBSE.
Thank you, Ali. So it will be my pleasure to present the next or the first application of search-based software engineering, which is tackling the problem of performance regression. So to introduce this problem, the problem of performance regression is actually results in the big family of regression testing. So regression testing is the art of detecting any anomaly or abnormal behavior that the software can experience throughout its evolution. And performance regression is a critical subset of regression testing where we care specifically about execution time. So in this testing process, we care about capturing any code changes that may introduce anomalies in the execution time of the software in terms of speed ups or slowdowns. If we take, for example, this example that we see here, we have this timeline of execution time along with several code changes, and we can see that we have experienced some sort of slowdown in the commit number 45686, right? So after submitting that commit, which is 45685 actually, we have experienced a slowdown in the system. So while speedups may not be bad news for developers, slowdowns definitely are, because slowdowns will be hindering automatically and drastically the user's experience. Therefore, capturing them becomes really important for software testers. So unfortunately, the problem of performance regression testing is such a difficult one. Why? Because a lot of code changes that can be sort of intuitive can easily introduce performance regression. Let's take this example. In this commit that we have extracted from the Git repository, a developer has moved a given static attribute, which is here p-value known, into a struct. It was moved into a struct, and by doing so, they have introduced a performance regression. Why? Because now accessing that attribute has become more expensive, and therefore during the execution it will take more time to get the values from that struct. And therefore a simple change in the source code can be responsible for performance regression. So what would be the perfect solution for this, right? So if our problem is to find such code changes, which we call changes introducing performance regression, so ideally speaking, the best solution for this problem and the optimal solution for this problem would be to simply test every code change for performance regression. And it's always important, perhaps in SBSC in particular, and generally in optimization in general, is to sort of define what is the optimal or naive solution and why it may not work. And clearly for this problem, this optimal solution of testing for performance every code change is theoretically complete, but practically it's unfeasible. And this is for the following reason. So let's take, again, the Git project as an example, and let's look at us testing for performance of all the code changes between version 2.20 and 2.21. So this is the version we're looking at right now. So, and this between the 220 and 221, we have experienced 446 commits. So optimally speaking, we need to test every single code change of these commits. And to do so, we will have to run around 5 benchmarks. Well, the number of benchmarks may differ from one commit to another depending on what context these commits are, what are the files associated with those changes. But on average, we can test up to 5, or on average, we can test 5 benchmarks, or what we call performance test cases. And these benchmarks, they can take up to 2 hours to execute altogether. And if we do the math, for 446 commits, running 5 benchmarks that take around 2 hours, this will take up to 30 days of performance testing. Bottom line, performance testing is extremely expensive. Therefore, unfortunately, we cannot perhaps perform it at the commit level. We cannot just test every single code change. And therefore, we have to now sort of come up with heuristics to decide about how should we do this performance testing now. And therefore, if you look at how multiple projects do that, so if we take the example of MySQL, so the way the performance testing team does this is they test performance testing, they do the performance testing per release. So they would come by the beginning of each release, and they would run their performance tests. The Chrome project, they do it differently. So they do this every 4 revisions, right? So for the Linux projects, they do it almost every week, right? So as you can see, different teams, they may have different testing strategies, and all of them are sort of heuristics, because by the end of the day, developers will submit a lot of changes, right? Then they will test for performance while keeping their fingers crossed that they did not introduce a performance regression. Because if they will detect that there is a performance regression, they will have to go back and rewound and revert various commits, searching for the root cause of that performance regression. And this can be a nasty task, which is time consuming and human intensive. So for that reason, the goal of this research is to sort of come up with a way to help us better prioritize code changes for performance testing, so that we can help developers appropriately capture performance regression. So how would we do that is by sort of profiling code changes and trying to see whether a given code change might be closer to the benign changes that they don't introduce performance regression, or it is sort of closer to the problematic ones, and that way we can prioritize performance regression accordingly. So let's look at how this works. If we have, for example, this timeline of commits, which are several code changes, so the ones in green, we can see them as benign, typical, they're fine, they don't introduce performance regression, while the red ones here are problematic. So given this history of previously known commits that either they are problematic or not, if we have a new commit that has been already submitted to the system, we can make a decision whether this commit is going to be safe or is going to be problematic. And if it is problematic, it is most likely that we have to prioritize it for performance testing. So instead of us relying on heuristics, which to say, okay, we should test every release or every week, we can say we should test every time we detect a potentially problematic commit. So How do we then profile those code changes, right? So this is a good question. So how do we do that? So what we can do here is we can take a commit, we can diff it to the previous commit to look at all the changes that has been done in that commit, and then try to come up with sort of a signature to that commit. We can do some measurements, and those measurements will give us sort of a blueprint for that change, right? So that blueprint would define exactly whether this change can be problematic or not. And how can we do that? We can, for example, rely on metrics. Okay, so those metrics can help us come up with measurements in the source code that will tell us, and they can profile or characterize a given code change. And we can use that information or those metrics as a way for us to develop a model that can help decide about whether this commit is problematic or not. Let's look at how this works. We take now a diff of a commit. We can calculate now some metrics. We can look at various metrics, and we'll see later what metrics I have used for the study. We can look at metrics such as complexity, coupling, cohesion, etc. So these metrics can become a blueprint for the changes that happened in that code change. Then we feed those numbers to a detection strategy. This strategy will actually rely on a history of previously known commits to be either benign or problematic. It will take the values of the metrics, compare to the previously known values of metrics for the benign, the good commits, and for the metrics of the bad commits, and see to what extent it is closer, or these new values are closer to which group, right? And according to the closeness to which group it belongs, we can decide whether this commit is fine, sort of fine, it's safe, or this commit is dangerous and it needs to be tested. Okay, so now the question is, how can we develop this detection strategy or this solution? So in our recently accepted paper in the Symposium of Search-Based Software Engineering, we have used optimization to develop that model. And let's look at these details. So my next presentation will be telling how did we develop that detection strategy. So what we have done in a nutshell, in a black box manner, we have taken as input the code that we want to test for performance, right? It's a code change that we don't know whether it's problematic or not. We will feed it into a model, and this model has been already deployed has been designed and generated by an SGA2 in this case. This model will take into account the history of previously known commits, either they are problematic or not. It will also take a list of static and dynamic metrics that we will be using to characterize those code changes. And then, of course, it will also take into account benchmarks, test cases. And then it will come up with an output, which is binary. It's a decision whether we should test this piece of code or not. So now let's unbox this black box and see how did we implement this solution. So what we do is we have three different phases. The first phase is we call the collection phase. So in this collection phase, we'll look at the history of previously known commits. And by known, I mean they are known to be problematic or not. So we sort of know that this commit has been known to be problematic and this commit has been known to be safe. So we take each commit and then we run the benchmark to calculate some numbers. Right? The static analysis, we do some static analysis and dynamic analysis, and we calculate those metrics, static metrics and dynamic metrics. We feed those numbers to an SGA2 to sort of come up with a detection rule that will tell us for this pattern in the metrics, right? This commit is sort of close to the either the good commits, the safe commits, or to the problematic commits. So we are sort of developing and designing a decision tree where we can use the metrics that we have calculated and their corresponding thresholds to sort of detect whether this commit is problematic or not. So once we develop that rule, then for a given new commit, and this is the detection phase, so now we can deploy this model, and for a new commit, we can calculate the metrics and then run it against the model, and then we would say whether this commit should be scheduled for performance tests or not. So To do or to implement this solution, we will rely on the following metrics that have been widely used in the previous literature. Some of them are static, such as the number of deleted functions, the number of added functions, and some of them are also dynamic and static, such as the number of deleted functions that are reached by the benchmark during the execution time. So we have a variety of metrics, and clearly this is not an exclusive list of metrics. So we can actually test many more as long as they can perhaps improve the accuracy of the model in the future. So as we have previously seen in the previous section, to define a problem as a search-based software engineering problem, it's important to follow the following formulation. So we have to define the solution representation for the problem, and then how do we evaluate the solution, and then how do we evolve the solution. So for the solution representation, our solution is clearly a decision tree, which is a combination of operands and, of course, leaves. So we are looking at the appropriate combination of metrics and their corresponding threshold values to make a decision whether this commit is problematic or not. And clearly here we are looking for making that decision, binary decision, whether this one should be tested or not. And this is sort of how we encode our solution. Then, in order for us to evaluate our solution, we will rely on two objectives. The first objective is what we call the hit rate, which is the number of correctly detected commits, the total of number of commits encountering performance regression. So we are sort of looking at whether we have made the right call to say that this is a problematic commit or not. The second objective, which is the dismiss rate, is our ability to look at a commit and say, no, this one is safe. Right? So looking at, again, the ratio of how many times we have called a right call and said, yeah, this one should not be tested for performance, and we're correct about that. So if we do the initial analysis, that this is on the right-hand side of this figure, of this screen, we can see that these two objectives are conflicting, which means that when we optimize for the hit rate, the dismiss rate becomes really bad, right? Similarly speaking, if we really optimize the dismiss rate, it will automatically hinder the hit rate. And therefore, these two objectives are found to be conflicting, and this justifies the use of the multi-objective optimization for this problem. Next, we will look at how we will evolve the solution. So to evolve the solution, and since we are using NSGA2, we have to implement and encode two recombination operators. And the first one will be the simulated binary crossover, the SBC, in which we will actually take the decision tree that we have developed from the parent 1 and parent 2. We will come up with a split. Then we can exchange, the trees to create our offsprings. As for the mutation, we will use a polynomial mutation where we can randomly select a leaf, like for example this one, and we will replace, for example, the value here by another value, or we can take, for example, another metric and replace it with another one metric randomly and replace it with another metric. And this is how we can also mutate the solutions. So after defining the solution representation, evaluation, and evolution, then we are ready to develop the model. And to do that, we have used an existing data set of known commits. So we have taken from the Git project 713 commits. We have used 5 benchmarks to test them, and we have used 2 static metrics and 5 dynamic metrics to do this analysis. And then we have tuned these parameters for NSGA2 so that we can get the best results, or the best results when we evolve the solutions. So to evaluate our solution, we have looked at 2 main research questions. So the first one is, to what extent the solution provided by NSGA2 can outperform state-of-the-art solutions. So we are sort of doing a comparative study between NSGA2's performance with other performances of other potential algorithms that we can compare against. The second research question looks at to what extent this generated model or solution can survive the waves of various changes throughout the software evolution. Because again, some models may be able to survive for a long time, some others may not be able to survive some time. So we want to see how long it would take for our model to become deprecated, sort of. So for the first research question, We have performed the comparison in terms of hit rate and dismiss rate between NSGA2 and Perfecy, which is one of the state-of-the-art deterministic algorithms to characterize performance regression, introducing code changes, and also we tested against the KNN algorithm. And clearly for those results, we can see that Perfecy and KNN are sort of comparative to NSGA2, at least for the dismiss rate, especially KNN, right? So, and what we mean by dismiss rate is we are able to decide or correctly identify the benign commits. However, for detecting the problematic commits, our NSGA2 was able to properly to characterize those changes, and it gave us the best results for the hit rate. So for the overall combination of both, if we look at the F measure to combine both, we can see that NSGA2 has given the best trade-off between both solutions. And as you can see here, if we try to sort of interpret those results, right? So if we are not performing well in the dismiss rate, it means we are actually recommending good commits to be tested, which we are wasting computation time into testing. However, if we are making a mistake in the hit rate, we are considering problematic commits to be benign, and this will introduce performance regression in the system. So sort of in this case, for this problem, the hit rate is way more important than the dismiss rate. And again, but if you look at this also, if you interpret the results of NSGA2 in practice for this F measure, we can see that we are sort of hitting an F measure of 0.5. You know, our results are oscillating between 0.04 and 0.06. So even though NSGA2 was able to perform or outperform existing studies, we are still far away from being able to provide a production-ready solution. Because in practice, developers would not trust a model that would simply come up with the best solution with the probability of 50%. So we are wrong 50% of the time. And this is still a problem that we need to work on, and we try to also improve to improve the accuracy of our model, which we will try to, for example, increase the number of metrics that we can use, and also try to look at what else we can do to better characterize performance regression, because it is by nature a difficult problem. So for the second research question, we try to look at how long our model can stay performant or can keep its performance throughout the various level of changes. So to do that, we have taken the commits in their chronological order. We have created 10 folds. So we split our commits into 10 folds, which will contain around 70 commits each. And then we will use the first fold for training and the remaining folds for testing. And when we do so, we notice that we experience a decrease in the performance of the model throughout time. And this can be explained by the fact that as software evolves, more files are being added to the system that this model is not aware of anymore. So therefore, it is important for the problem performance regression to sort of also detect when our model is no longer maintaining its performance, so that we can rerun the model and we can recreate the model, or we can reinforce the performance of the model. So this is our first contribution in which we show how we have taken a problem from software engineering and how we follow the 3 steps of solution representation, solution evaluation, and solution evolution to define how we can define this problem into a position problem. And then we have shown how we can interpret the results of this problem through these 2 experiments. And next, we can move to the next second contribution, which is the application of search-based software engineering for the problem of web service design. And my colleague Ali will take over to do this presentation.
Indeed, it's extremely important to pay attention when changing the source code of a software system to avoid performance regression in practice. And at the same time, developers should pay attention as well to avoid poor design and implementation solutions, either when changing their source code or in the initial design. So in the next SBSC application, I will show you how SBSC can be applied to solve design problems in web services at the design level and at the source code level. So before delving into the details of our approach, let me start by giving an overview about service-oriented architecture, or SOA for short, for non-familiar people. So today SOA is one of the popular technologies for building software systems. And looking at SOA, it is not an architecture and it's not a system. SOA is rather a way of designing a system. This is an approach to system development and an architectural style and a design paradigm. So the leading technology today used for implementing the service-oriented architecture is web services, and we can build software systems using coarse-grained components or services that can be used by many applications running on different platforms. For example, for a travel system, we can reuse multiple services that are provided by third-party providers, such as a car rental service or a flight service, hotel service, or a payment service. And all of these services are running on different platforms and are invoked remotely. So if designed well, web services can bring a lot of advantages, such as reducing the development cost by reusing existing services that are implemented and provided by third parties. It can also bring interoperability, agility, adaptability. And here the hardest part is if the designed well. So, and how to adapt SOA correctly. So how to do all the upfront work that is required so that these benefits can be achieved. So in the next set of slides, I will provide an idea of what we call bad design practices in service-oriented architecture, and more importantly, how to avoid these bad design practices. So poor design can manifest in the form of what we call anti-patterns, which can exist in web service interfaces. So an anti-pattern is defined as a symptom or a set of symptoms of bad design practices and poor implementation choices. For example, there is the fine-grained web service, which is a small web service with a few operations implementing only a part of an abstraction, and it often requires several coupled web services to complete a functionality, resulting into a higher development complexity and reduced reusability. And on the other side, or the other extreme, we found the God object web service, which is also called multi-service, which is a web service that have a lot of operations in its interface that are unrelated. And this kind of web services are characterized by low cohesion, high response time, and often it's unavailable or have low availability, since it's invoked by many clients, and it's not easy to reuse since it corresponds to several unrelated functionalities that are implemented into a single large interface. So let us see a real world example, which is the Amazon Elastic Compute web service, EC2. So this web service exposes 87 operations into one single interface, and the WSDL, the interface documentation, it have 4,000 lines of lines in its documentation, and over 800 pages of API documentation. So this interface implements several functionalities, such as image management, instances management, security, also snapshot management, and many other functionalities, and they are all in the single interface. So here obviously there is a problem with the design of this interface, and we need to refactor it. We need to improve its design so that we can keep each functionality in one single interface instead of putting everything into one large interface. So actually there are few books that attempted to provide a catalog of web service anti-patterns, and some existing works that attempted also to define semi-manual rules that can detect these anti-patterns using combination of metrics and threshold values. They try to translate the definitions from these books into detection rules using specific format and domain-specific language. So the problem, however, in practice is that it's difficult to define or express such detection rules because simply there is a large list of anti-pattern types that we need to characterize. There is a large exhaustive list of quality metrics that we need to look at in order to characterize each of these anti-patterns. And also for each quality metric, there is a large number of possible threshold values to be associated with. So here we observe that there is a huge search space to explore, and we need an expert to manually write and validate these detection rules. And to make the situation harder, there is no consensual definitions of anti-patterns, and so that we can find divergent decisions about each type of anti-pattern in practice. So our idea to address this problem is to infer detection rules from anti-pattern examples, real-world instances of anti-patterns, using combinatorial optimization. So to solve the problem, we proposed a search-based approach to automatically detect web service anti-patterns, which has been published in IEEE Transactions on Services Computing back to 2017. Then we extended this approach later to improve the performance. So our solution to this problem is it takes as input a base of examples, real-world web services that are infected by anti-patterns. Then we considered a metric suite so that we have multiple quality metrics at the interface level or at the code level, and also we consider dynamic metrics in order to characterize the symptoms of anti-patterns. Then there are two search algorithms that are executed in parallel to identify anti-pattern detection rules. And so the first aims at identifying or at generating rules, and the second aims at generating detectors, and so that we can have a fitness function between them, so to make an intersection between both algorithms. The idea is to reach a consensus about the detection of each anti-pattern type. Then for our metric suite, which is fundamental for the detection of our anti-patterns, so we considered three types in the interface level and also in the code level. We basically from the code skeleton, and also we considered one dynamic metric. So of course this is not an exhaustive list that we can extend later with more quality metrics and also more dynamic metrics that like quality of service, also related attributes. So to infer our detection rules, we used genetic algorithm. Genetic algorithm can learn or can explore this list of quality metrics, and can also explore the interval of threshold values that are associated with each quality metric. So to adapt genetic algorithm, we need some key elements to be defined for any problem, like the solution representation or solution encoding, the definition of the fitness function, and also the definition of genetic operators such as the crossover and the mutation. And also we need to properly define or generate our initial population to be evolved to converge towards the optimal solutions. So suppose that we have a base of examples that consists of several anti-pattern types, and then we have a list of quality metrics. So for each quality metrics, we have some possible quality, some possible threshold values with lower bound and upper bound, and we need to pick up or to find the right threshold to be associated with. Like, for example, if the number of declared operations in the interface exceeds a certain threshold, so this becomes risky and can be detected as an anti-pattern. So as for this rule, for example, we considered the tree representation where we use a tree-based encoding where the leaves are combinations of quality metrics and threshold values, and nodes are logic operators such as and or. So for example, for this rule, if the cohesion is less than 0.5 and the number of pore types is higher than 3, and also if the number of simple types is higher than 41, or the number of complex types is less or is higher than 32, so this is likely to be a God object web service. So these rules are trained and inferred generated from our base of examples. For the fitness function, we evaluate how good is a rule based on recall and precision from our base of examples. So for the crossover, we used random. For the mutation, we change either a leaf or an internal node. We select randomly either a leaf or an internal node, and we can change either the metric or the threshold value, or we can change the logic operator. As for the mutation, we select randomly two subtrees from two random solutions, and then we switch them to generate two offspring solutions. So and then both solutions will be put and to the next iteration of the genetic algorithm. So to evaluate our solution, we mainly defined 4 research questions. So for the first research question, we looked at, or we compared our solution PUA to genetic programming, the canonical genetic programming, genetic algorithm, and random search. As for the second research question, we also compared, we also looked at to what extent can our proposed approach detect web service anti-patterns. For the research question number 3, we also looked at possible bias towards the detection of specific types. We looked at the differences in terms of performance for each type of anti-patterns. And for the last research question, we also compared our approach to a recent or to a state-of-the-art approach for detecting web service anti-patterns. Then for the evaluation, we used a benchmark that is composed of 425 web services that belongs to different category like financial, science, search, shipping, travel, weather, and other categories. And our dataset is also available, publicly available to further extend it or replicate our study. We also considered various types of anti-patterns like the God object web service and the fine-grained web service that I described earlier. We also considered the chatty web service, which is a web service with a high number of operations that are typically attribute level like setters and getters. This anti-pattern may have also fine-grained operations which degrade the performance and lead to high response time. We also consider data web service, ambiguous web service, redundant port types, CRUD interface, and maybe it's not RPC web service. So for the training, for the validation, we use a tenfold cross validation to for each category of or for each category of web services in our base of examples or our training data set. Then for the evaluation metrics, we used recall and precision. We also compared our approach into state-of-the-art approach, SODA, and another approach in 2015, which was initially presented in GECCO 2015 to infer detection rules for web service anti-patterns. So as for the results, we see here the box plots for each category of web services, and in terms of precision, we observe that our approach POA is higher than the other than genetic algorithm, genetic programming, and random search. In almost all the categories, we can observe similar performance for some of the approaches, but overall, as we see from the figure, it achieves higher performance in both precision and recall, which makes us confident that a search-based technique is efficient when designed well and when considering the different symptoms that we can explore. As for the overall precision, so we found that on average we have 89% in terms of precision and 93% in terms of recall in all the data sets from the different category. We observe also that the standard deviation is not high, and we can detect web services with equal or with almost similar performance across the different categories. As for the third research question, which is about the sensitivity towards anti-pattern types, we investigated the anti-pattern type that were detected to find out whether there is a bias towards the detection of specific anti-pattern types. So our goal is to make sure that we can detect all of them equally. We observe here from the figure that we have so low variability in terms of both precision and recall across the different types of anti-patterns, and which is actually an interesting finding, so that search-based techniques can work efficiently under different symptoms and different quality metrics. And as for the last research question, we investigated also the performance of our approach as compared to two other state-of-the-art approaches, and our approach which appears in the yellow color is higher or is better than both state-of-the-art approaches in all the anti-pattern types that we considered, which is actually an interesting finding, and can also show the rules to the developers so that they can see what are the most important factors or the most important features that they can look at when changing their code or when designing their initial application. And so that's good. So here we can detect our anti-patterns, we can identify them from any web service. Then most importantly, the problem is how to refactor them. How can I fix these anti-patterns to avoid their impact on all the clients that use them? So to fix these anti-patterns, we proposed an approach to mainly to addressing one of them, which is the God object web service. So in our recent work, we proposed an optimization or multi-objective optimization based approach to find the right or the best modularity of these web services. For example, when we have a God object with multiple operations, we can, or the aim is to find or to split it into multiple interfaces so that each interface can implement a single abstraction at a time. So let us go back to our real-world example from the Amazon, which consists of 87 operations in its interface and over 800 pages in its API documentation. So developers are encouraged here to refactor and to review their interface to provide best practices of third-party reuse. So here obviously there is a need to redesign, to restructure this interface. So also there is a common problem in web services. So a recent study showed that that 81% of service provides only one interface for Amazon, and all the services also in Yahoo expose only one interface, one large interface. So we decided to focus on Amazon and Yahoo Web Services to evaluate our approach. So what we considered is our solution consists of multi-objective optimization using the non-dominated sorting genetic algorithm NSGA2. So we take as input a web service interface described as WSDL, Web Service Description Language. Then we parse the interface to extract both structural metrics and semantic metrics. Then we used WCRM, which is Web Service Interface Remodularization, the name of our approach. Then the goal is to identify new interface modularization. This means that we want to restructure or to split up the interface into smaller interfaces that are more cohesive and loosely coupled. So here our search algorithm that we used is NSGA2. Of course, we compared multiple algorithms to find the right or the best one. Our solution representation is a vector where in each dimension we have an operation that is assigned to an interface. And for our objective functions, we considered three conflicting objectives. The first one is about maximizing the cohesion. The second objective is to minimize coupling, and the third objective is to minimize the interface modifications. So the last objective is to control our modifications, as we do not know to deviate a lot from the original design. We want to keep as much as possible with the original design while improving cohesion and coupling. For crossover, we use a single point crossover, and for mutation, we randomly select one or more dimensions and replace them by other dimensions. So that, for example, operation 2 was assigned or the operation 6 was assigned to the interface 2. Then we change it to interface 3 by mutation. And also we used several cohesion, so a service interface, we like sequential, we used sequential cohesion. A cohesion or a service interface is sequentially cohesive if it includes pairs of operations such that the output data produced by one operation are used as input for the other operation. So here we can see in the figure so that the output and input can have are used in a sequential way. As for the communication cohesion, so this we can assume that two interface operations have communicational cohesion if it includes pairs of operations that operate on the same either input and output data. As for the semantic cohesion, we look at the names to identify pairs of operations that use similar identifiers or names. This means that they implement similar abstractions or they are related in the same functionality. So we combined these three cohesion in order to find or to converge towards groups of operations that have similar sequential cohesion, communicational cohesion, and semantic cohesion in order to best split our interface. Then for the research questions to evaluate our approach, we looked at mainly two research questions. The first research question is about the impact of the suggested remodularizations to the interface design quality, and the second research question is about the quality of these suggested remodularizations from a developer point of view, because it's important actually when you do such changes in the design level to have the opinion of the developer, because you can improve cohesion, for example, or you can improve coupling, but more importantly, it should make sense from a design point of view. That's why it's important to see the developer point of view. So as for the evaluation, we considered a benchmark of 22 web services that are provided by Amazon and Yahoo. And also our dataset is publicly available in the link here in GitHub, so that you can check it and you can extend and replicate our study in this dataset or on other web services. As for the evaluation method, we considered three quantitative measures, which are cohesion, coupling, and modularity. And also we considered for our second research question qualitative measures to see whether our remodularization are similar to other remodularization done manually by developers in terms of precision and recall. And here we assume that if we provide similar solutions that are inferred or that are identified manually by developers, so our approach could be practical and could be accepted in practice. In addition, it's important also to look at some baselines. So we compared our approach against two existing approach, SEAM, which is published in 2016, which is the graph-based partitioning using deterministic approach, and also we compared with the greedy algorithm to see what advantages can our approach bring as compared to these two approaches. So for the in terms of cohesion, we found that the greedy algorithm is the best as it tends to generate more interfaces, so they are more cohesive. But looking at coupling, we found that our approach is the best. So as a balance between both cohesion and recall, the modularity metrics reflect better this trade-off, and we clearly see that our multi-objective approach can achieve such trade-off of having better, which is better than traditional graph partitioning and also better than greedy search algorithms. So we observe here for the second research question, as for the qualitative evaluation, the results indicate that the multi-objective search achieves also higher precision, which is higher than 70% in all the considered web services, and it also achieves sometimes 100% in terms of precision and recall. And we can see that we can split for example, the Amazon Web Service, the largest one, it can be split into 22 web services or web service interfaces. Sorry, and here we see also the qualitative evaluation from the developers, and we can see that we have our approach WCRM have more acceptance from developers' point of view than the other greedy search and graph partitioning approach. And also to see how we can identify the interfaces that are extracted by our approach. We show again the elastic computing service provided by Amazon, and we can see here that there are several interfaces, and each of them implements one abstraction at a time. And so this can make the service easy to reuse, easy to modify, and easy to understand by developers. So so here are our refactoring changes, and we have these suggested refactorings or remodularization changes. A developer can apply them. Of course, he can decide to refine them if needed, but the problem is who should review these changes before they are implemented or before they are merged into the code base. And this is important because bad changes can affect again the performance. The regression can have some regression performance as presented by Mohamed Ouam in the first contribution, and also can lead again to other anti-patterns. So it's important to make sure that these changes are well implemented and do not have any regression. So for the next contribution, Mohamed Ouam will be presenting reviewers' recommendation for modern code review. So yeah, please go ahead, Mohamed, for the next contribution.
Thank you, Ali, for this presentation about all the problems that we can experience in web service design. And perhaps one way to avoid having those anti-patterns in design is to also pay attention to designing code appropriately and also reviewing it appropriately. So in this context, code review has been also evolving as software engineering practice to also support maintaining high quality of code. And the next presentation or the next contribution, we will see how code review as a solution and as a practice can also be expensive on itself, and how we can, using intelligent algorithms, can help the cost of code review and to make it more accessible for companies. So in the next contribution, let us start with talking about the background of code review. So let me start with giving you the overview of what we call the traditional code review, which has been practiced for many years already. So code review is a key part of software development, as we said before, and it's important to ensure software quality. The traditional code review or code inspection, per se, was mainly a manual process and done through in-person meetings to discuss, discuss the code and the potential revisions and whether it actually fits the appropriate changes that are required by the requirements or by the bug fixes, and whether the implementation of those changes matches the standards of the project. So, however, such formal process is not always possible, especially with the nature of distributed development that we experienced recently, where developers sometimes are in separate places, separate time zones, etc. So today there is a high tendency to use what we call the modern code review, which is a lightweight, less formal, and tool-based process that actually now is already being in practice and adopted by both industry and open source systems. So to take a look at that, we can see a developer here submitting a code change to be merged with a code base. But before this code change even reaches the code base, it has to go through the modern code review process, where we will have here a bunch of developers that are also serving as reviewers to this code. And one of these developers or multiple developers are assigned to review that code. And if they discover that there are some anomalies in this proposed code, either through testing it or through verification of whether it meets the code standards or not, so they will ask the original author to do some rework on the source code, to do some updates, to do some changes, some refactorings, etc. These reworks sometimes may lead to even rejecting the code in case the code does not really meet the requirements and it's not performing well, or it's maybe introducing some bugs, or it may lead to also being accepted, maybe after some rounds of rework. And once the code is accepted, that's when it reaches the code repository. So this is the typical optimal process for code review. However, there was always challenges with that. But before we talk about the challenges, let's look at some example of how this code review looks like. So if we take this example here of a potential code review, so we can see the change ID here, number. We can see that the author here has provided some description of the intention of the code change and in sort of a description. Then in the right hand side here, we can see the actual developer or the author of the code change. Here we can see the actual reviewers who are assigned to validate this code change. And here we can see all the changed files that correspond to this piece of code that these reviewers. However, as any practice, it will have its own challenges. So if you're searching for reviewers for a smaller project with a smaller team, it would be easy to find appropriate developers who would be able to have the appropriate knowledge in the source, the code base, to be able to review potentially any source file in there. However, as teams grow large in numbers and also software systems grow large in size, in components, it is becoming harder and harder to find the appropriate developers who may have the appropriate knowledge to actually evaluate that piece of change for that given component. So therefore, finding the appropriate developer for a given piece of code to validate has become on its own a challenge. And therefore, various studies have tried to also help with that problem by recommending the appropriate developers that can do the code review. So these studies, technically what they do is they try to look at how can we measure the expertise of a developer and the appropriateness of a developer for a given code change. Okay, so they would look at all the changes performed by all developers and try to see what are the appropriate developers that would be able to understand, comprehend that piece of change, and also what developers were actually working on the files associated with that piece of change. So those developers are most likely to be able to review this code properly and would potentially capture any anomalies in that change. However, all these studies that already been given, while they are potentially good solutions or initial solutions for the problem, they all suffer from one fundamental concern, is that they would treat the reviewers independently and they would recommend them separately from each other. But if we refer to the example that we have seen earlier, we can see that we have actually recommended a bunch of developers or a set of developers instead of only one. So sometimes it would make sense for us to recommend multiple developers at the same time. And this on itself would be a problem. Why? Because naively speaking, if we want to look at what would be the appropriate solution and the optimal solution for this problem, we have to explore all the possible combinations of developers that would be appropriate for that code review, and clearly this is a combinatorial problem. So therefore, this is where SBSC kicks in, and we can perhaps tackle the recommendation of a subset of developers as reviewers for a piece of change, as an optimization problem. And this is sort of where our idea comes into the picture. So here we take this heuristic search to optimize both expertise and also the social aspects, which we will talk about in a second. So we will add another dimension also to evaluate the appropriateness of developers to review code. So besides their own changes and expertise in the source code, we can also look at their history of reviews to also recommend the appropriate developers for a given code review. Let's take a look at this. So what we are proposing here is what we call the review recommender. So what we will do is we will take a developer who is requesting a review for a given piece of change, and then we'll look at the review history and we feed all these information as input to our solution. This solution will look fundamentally into two different dimensions. The first dimension is the reviewer expertise, and the second dimension is the reviewer collaboration, and they would combine these two together to recommend the appropriate reviewers for that piece of code. Let's now look at how this works from the inside. So we model the expertise of a reviewer as follows. We look at their comment frequency, and this is making the assumption that a reviewer who is expert in code is someone who would frequently do changes in the source code. This is sort of our assumption. And also we will make the assumption that a reviewer is also expert in the code if they are changing or making recent changes, right? So here we are making the assumption that someone who has been changing the code recently, like for example, this month or this week, would be more expert than someone who has changed the code 10 years ago. So we are ranking developers then based on their expertise, based on their change frequency and change frequency. Another dimension we look at is also the previous history of code reviews. So we will look now at the socio-technical aspect of relationship between reviewers and each other with others. So what we will do also, we will look at the history of previous reviews for each developer and each reviewer, and we will develop a graph that will tell us how many times two developers has already been found to be together in a given code review. For instance, if we look at this graph here, we see that Stan and Carol here, they were both involved or they have been submitting comments to each other 41 times throughout their history of the reviews to each other. So here we are developing all the interactions, or we are modeling all the interactions between Stan and Carol, for instance. Either one of them is the reviewer and the other is the author, or vice versa. So this will tell us sort of how the degree of interaction between both, and this degree of interaction will define how close they are in discussion and how they are familiar with each other's opinions and the intelligence exchange files. So most likely, if two developers have been already involved a lot in reviews, they're most likely to evolve again when this happens one more time. For instance, this also graph will be interesting because we can detect when for instance, two developers have never interacted with each other. For instance, here we can see that Victor and Carol, they have never been involved in any code review whatsoever. So they are most likely not to be able, so most likely that Victor and Carol would not be appropriate for each other if one of them wants to review or need a reviewer for another. So this is how we can also detect quickly that we have some disjoint nodes in our graph. So combining these two features, one of the expertise and one of the collaboration, it would help us perhaps know what are the appropriate developers and rank developers based on these two scores. So what we will do here is we'll create solutions, multiple solutions. Each solution will be a subset of developers that we can recommend, and we will hope that we will maximize a fitness score which is based on expertise and collaboration, right? And we want, by the end of our evolution, to actually only recommend the correct set of reviewers that have the highest score of collaboration and expertise for a given code change submitted by a given code change author. So let's look at how we did this adaptation. So we encoded our representation by selecting all the potential reviewers, all of them encoded as a vector, and then we will encode each one by either 0 or 1, each dimension by either 0 or 1. 0 meaning that this reviewer will not be selected for this code review, and 1 being, yes, this reviewer should be selected for this code review. So in this example, per se, we are recommending 1, 2, 3, 4, 5 reviewers for a given code review. So what we'll apply as recombination operators is the crossover, which will allow us to recombine two solutions, and this will create a fresh set of, or a subset, or an offspring set of offsprings that will have a different variation of reviewers that we can recommend. And again, the mutation in this case would be able to perhaps take one dimension and flip it, so we can either take a reviewer that is recommended and we flip it to not recommended, or vice versa. We can take a recommender who's not recommended and recommend it instead. So the fitness function here is clear. We have the expertise from one side, and we have also the collaboration from the other side. And both of them are to maximize. So what will end up is our fitness will be the aggregation of these two measurements altogether. So to evaluate our solution, we have conducted 3 main experiments. One of them is to see to what extent our recommendation is able to actually perform what has already been done. So to see to what extent we are correct in our recommendation. And then we will see whether the new dimension of collaboration will be helpful for our given solution. And also we will see whether the choice of genetic algorithm is appropriate given the comparison with other search algorithms. So the dataset that we have used for the study is available in this link. Feel free to also use it in case you want to try to extend the study or replicate it. We have picked 3 different systems that are famous and they are popular, and they have their own typical reviewers. And as you can see, we are looking at a lot of reviews and also a lot of reviewers as well. So this makes the recommendation a bit hard for these projects. And we also use as measurements or performance indicators, we will use the accuracy at K, which are, since we are looking at a top K reviewers to recommend, we will test whether we are appropriate to recommend the appropriate reviewer at 1 when we are recommending only 1 reviewer, or when recommending 2, 3, 4, 5, etc. Also, we look at the ranking performance using the mean hierarchical rank, and also we will test against other existing approaches as well. So for the first experiment, we can see that our precision and recall were pretty high compared to other techniques. This will tell also that the choice of our algorithm is adequate for this problem. Here, for instance, we are averaging a precision of 50%, which can be seen as necessarily not a perfect number if you want to deploy this for developers. So we are still in need of better measurements and dimensions to better profile reviewers for a given code change, but still we are performing better than existing studies, so that would be acceptable from that aspect at least. And then also our recall shows that we are able to capture the appropriate developers as much as we can if we are recommending more than one developer. And we are achieving, of course, better than other studies. So as a summary, our approach is correctly recommending peer code reviewers with an average precision of 55% and a recall of 70%. And then when it comes to the new dimension collaboration, what we have done is we have taken the genetic algorithm and we evolved it using only one subset, which is one score, which is one objective, which is the expertise. And also we have created another instance of the genetic algorithm and we have only evaluated it with the collaboration. And we are showing the combination of both. And we can see that the combination of both performs better than having each of these objectives separated. And this shows the value that we can add when we add the collaboration dimension. And then also when we have tested our technique against other search algorithms, we have found that the genetic algorithm was a good choice since it performs the best across other search algorithms. Yet, as we have seen already, even though we are providing good results compared to other search algorithms, we are still behind developing a mature model which can be accepted by industry yet, because we are still behind in precision and also in a bit in recall. And also there is an important aspect that we are not capturing right now, because our model is actually providing some biased results towards expertise. And this bias is not necessarily practical, because developers who are typically experts are also the busiest developers in the company. So you may be able to quickly profile someone who is doing a lot of changes in the code and they're expert, and those people are typically very busy and they have already a busy schedule. So recommending them all the time for all the existing code reviews may not be practical. Therefore, it is important to also consider the workload of developers as another dimension when we are recommending reviewers. So we should also balance and find the appropriate trade-off between expertise and availability of reviewers. And to do that work, we have already presented our initial study that tries to find the balance, the appropriate balance between recommending expert versus available reviewers. And that study has already been accepted as a short paper in GECCO 2020. So feel free, if you want to know the results of that study, feel free to reach out to that study.
Okay, so good. Now we have an idea about some real-world applications of SBSE. Let us now see how we can formulate a software engineering problem using SBSE and how to implement it. So we will be using one of the existing tools called MOA framework, which is an open source tool that provides the implementation of several search algorithms. So this is the link of MOA framework, and also I'm providing the link of our example today so that you can access the source code and on GitHub, and you can rerun or extend this example. So let me first of all show you MOA framework main web page and its features. And so this is the web page of MOA framework. It has the key features described in the main web page. Also there are more details about these features, and more importantly there is the list of provided algorithms that are ready to use, so that the developer can simply specify the name of the algorithm in his implementation, and the tool will run the problem instance with the specific algorithm indicated by the developer. And Also, there are some interesting examples with their source code, so that this can constitute a good starting point for people who are interested in formulating some problems using optimization, or using, in particular, MOA framework with some code snippets that can help having first executions quickly. Then this is the source code of MOA framework, which is available on GitHub, so that people can look at the specific implementations. They can also extend or evolve the framework based on new algorithms. So as for the our example today, so this example will also show how optimization can support software engineering and vice versa. So software engineering supports also the growth of optimization fields through open source optimization tools. So as for our illustrative example, let us consider a simplified scenario of software migration. Actually, software migration is a common problem today with in software engineering. So I will first explain the problem and the requirements, and then I will show you how SBSC can be used to solve this problem. So suppose a company has its own web application and wants to provide their customers with a mobile application. So this is actually a trend in today in software engineering, and most of the companies are trying to have their mobile application as it's more accessible actually to users, and it's more convenient. So the company wants to provide two versions, one demo version which is incomplete, and another professional or full version of the application. So the challenge is how to select the features or the functionalities to be implemented in each version, or to be provided in each version. So it's for the demo version, actually there are limited number of functionalities as compared to the full version, or to the full application. So the original application has a number of functionalities, the actual website, and it's not possible to implement all these functionalities in the mobile version, as this depends on some constraints, like for example performance, size, and other constraints like the budget. So each available functionality has two main aspects that should be considered, which are the cost and the business value. So each functionality has its own cost and its own business value when implemented into the demo version or into the full version. So in addition, the cost and the business value, they depend on which version of the mobile app is holding it. So for example, a functionality will have a cost of $200 and a business value of 30 in the demo version, but the same functionality can have a cost of 300 and a business value of 50 when it's implemented in the paid or full version. So actually this is common in commercial software applications, as the paid version typically provides better quality of service and may have additional non-functional requirements such as security, performance, and other quality of service related aspects. So finally, each version has its own allocated budget. So the objective is to select the optimal set of functionalities that provide the highest business value, but of course without exceeding the allocated budget. So in this situation, one of the ideal solutions is to formulate the problem as a multi-objective optimization problem. So the software migration problem that we will be solving in this case study is very similar to the knapsack problem. So except that we now have two versions, a demo and a full paid version, instead of single knapsack, to hold the required functionalities to be provided to the users. Let me now show you the source code, an example of implementation of this problem using MOA framework okay, so this is our source code of the example. So first of all, there is we need to have data, or the related data to our example. For example, here when we consider the software migration problem, we have 2 versions and we have let's say 20 functionalities to be implemented. So we need to indicate the for each functionality its budget and its business value. So here we have, for the demo version, we specify our budget. We have a maximum budget of $500, for example. And then for each functionality, we need to specify 2 aspects. The cost of implementing it and its business value. We denoted for B value here. So for all the functionalities, we need to specify these 2 elements. So we have functionality 1 till functionality 20. And the same thing for the paid full version. We have a maximum budget which is $1,500, for example, and for each functionality we need to have the cost and the business value. Of course, here for the same functionality, its cost and business value can differ from the demo and the full version. For example, functionality 1, it has 90 as cost and 30 as business value, but for its cost in the demo version, it could be different. So then once we have this data available and specified, we need to implement our program. So first of all, we will be using the MOA framework package, and we need to define a class. For example, we call it migration here, which implements a problem interface. So this is really an interface that is available with MOA framework. Then we need to define some attributes that are related to our problem. For example, here we need the number of versions. We need also the number of functionalities. We need also a matrix to record the business values and the costs of each solution. And then we have a table for the budget that need to be respected. We have also another method load, so that we can read our input data for our functionality. So this is like a method for parsing that source data file. Then the main component here is the solution. So as described earlier, we need to find, or we need to define the solution encoding. So in our case here, we are using the method solution, or new solution, which will return a solution. And we need to create a solution using constructor with 3 parameters. Actually, we have the first parameter is the number of decision variables, and then the second parameter is about the number of objective functions and the number of constraints. So each problem has its own constraints. Then for the encoding, we need to define the encoding of our solution. In this case, since we have multiple functionalities and each of them should be either selected or not selected, so we use the binary string which takes a length as the number of functionalities. So here there are multiple other solution encodings that are available in MOA framework, and to solve a problem we need to properly define the solution encoding for that problem. So for example, here in our binary string, if the solution or for each bit corresponds to a functionality, and if it's set to 1, that means we will select it, and if it's set to 0, that means we will not select this functionality to be implemented in the mobile application. So, and then it returns that solution. Then the second important component here is the method evaluate. So we need to evaluate each solution, and actually this is the fitness function or the objective function. we will get the variable, the decision variable. We will obtain it, and then we will define two tables, and each table for a specific objective function that will record for the demo and for the full version. Then first of all, we need to calculate the business value of each demo and full version, and then we have another loop here to check if we exceeded the allocated budget or not. So if the exceeded budget, or if we exceed the budget, the solution will be excluded. Then we need to implement actually our migration problem in the main method. We need to define some parameters. For example, here we need to select the algorithm that will be used so here in this case we selected NSGA2, which is one of the popular multi-objective optimization algorithms, and we need also to define the maximum number of evaluations, and some other parameters could be specified here. So these are the basic parameters. And then simply we can show we can run our algorithm and also show the values, or show the solutions that are returned. So let us try, for example, this problem. Let me run the main method and see what we can obtain from our data set. So this is the output of our algorithm. We observe that we have returned 4 solutions. So for example, for the first solution we have selected these functionalities. So functionality number 17, number 18, 19, etc. And this is the business value for the demo version and the business value in the paid version. Of course, we did not exceed the maximum budget that we specified in the data set. Like for the demo version, we have a maximum of 500, and for the full version, we have a maximum of 1,500. So here, as you know, for multi-objective optimization problems, there is a set of optimal solutions. There is no single solution. So here we are the algorithm returned 4 solutions with different functionalities to be selected. But here, each of them has its own business value for the demo and the paid version. And we can also change these parameters. For example, instead of NSGA2, we can choose NSGA3, or even another algorithm like SPUA2, and we can rerun again the algorithm to see what it will return. So of course, some algorithms that are faster than others or more performant than others. So we can wait for a couple of seconds. So here you can see that we obtained another set of solutions. We can also change here the maximum number of iterations. So for example, if we keep it on 500, we can see what we will obtain. So here we observe that we only obtained 3 solutions, smaller, with the fewer functionalities that are selected. So here these parameters need to be defined with trial and error, and in order to find the right list of parameters, and also the right algorithm, or the best algorithm to be selected for a given problem. So this is a simple example that I try to describe quickly in this tutorial. Of course, there are many other possible implementations for this problem or for other problems in software engineering, and I hope that this can be helpful for people who never used optimization to start with at least and implement easily a problem. And also you can go and look at the other examples that are provided in MOA framework and you can even run them like regression problems, genetic programming, and many other problems that are ready and already implemented in the MOA framework.
Thank you, Ali, for the demonstration. It was really good to see some hands-on practice on how to we can take a problem and define it as a SPSE problem. And now we should look at the challenges and future work with search-based software engineering. So of course, like any research field, there are many challenges and possible future research directions that we can explore. And let me give you or explore some of them with you. So the first challenge that we can face when we are applying SPSE is we have to need to make sure that we have the right problem formulation, right? So we need to select the right solution encoding and the right fitness function. There are key elements for any attempt to adopt the search-based software engineering. Also, changing the optimization algorithm may not necessarily change the output to be better. So there is actually no magic recipe for that. So every problem has its own context, and there is no unique algorithm that would work for all sorts of problems. So we do need to actually practice multiple algorithms, and there's always that sort of trial and error and that intuition that tells you that perhaps this algorithm is more appropriate for this given problem. And this needs to be perhaps better articulated in the future. We also need to make sure that the adopted algorithm is exploring well the search space and can converge towards optimal or near optimal solutions. There are multiple performance measurements and indicators per se that can also be used to help with that process, such as the hypervolume, the spread, the GDI, etc. So the framework that we have, that my colleague Ali has previously shown, does provide that sort of information in case you want to see to what extent your algorithm is performing well in terms of convergence and also in terms of diversity if needed. So now if we look at the challenges that we can face with industry, so there are actually many of them that we can iterate, and I have been iterating around a few of them in my presentation as well, and in this presentation that we have done, me and Ali. So the main challenge that we can pick right away is the non-deterministic nature and the stochastic nature of this algorithm, right? So developers and managers typically, they do not like when they cannot understand exactly how the evolution works, right? So this is one of the challenges that we always face when we are trying to convince managers and developers about the accuracy of our models. Also, a lot of the problems that we have been tackling, at least in this presentation, this tutorial, we have seen that they do not necessarily provide production-ready scores. You know, they are still doing fine in terms of research papers, but they are not mature enough to hit the confidence of managers. You know, like for the examples that we have seen in the tutorials for the problems we're tackling, our precision for say they are still averaging in the 50%, and this score may not be acceptable for a lot of people from industry back there. So this is another challenge that we have to work on, is how can we also increase the correctness of our model and even improve their performance in general. Another challenge with industrial people is how to convince them that we need to have an idea about the solution. Then we need to explore problem space and find solution that we seek. Often people from industry do not have any idea about the solution, and that is why they are trying to solve the problem. So they do not necessarily understand how the search space is composed, right? So also sometimes it looks a bit risky to convince them that we start with completely random solutions, and this randomness somehow would transform into something concrete that would actually work. So sometimes that's not necessarily starting from randomness, but starting with some seed solutions might help with that. Or we don't necessarily go from the scratch. If we can find some existing system that we can start from, that also will help them, or maybe they would help gaining their trust. There are also other challenges and several research directions that we can take in this field. For example, you may have noticed in this tutorial presentation that we addressed several software engineering problems independently, right? So the question is, how do we currently need to design special algorithms for search for each software engineering problem? For how long we would keep um, addressing these problems separately? And this is sort of unrealistic because science is about generalizability. So we have to be able to come up with generalized solutions that can go across multiple problems. It's specifically for software engineering because these software engineering problems and activities, they have a lot of things in common. They have many patterns and many characteristics and many similarities. For example, selection problems or permutation problems may share several characteristics, so why don't we leverage that and we come up with a unification for these common patterns? Why don't we propose solutions that can tackle more than one problem at the same time? And this also takes us to the next challenge, since we are also currently addressing several SVE problems without really looking at the relationship between them. For example, testing, refactoring, code review, and code recommendation, these solutions, they all look independent, but actually they all fit together in the same maintenance process, and they have their own relationships, and they also impact each other. So as long as we are proposing solutions that are independent and they are not taking into account what happens behind the scene, we are also missing some piece of information that would have helped us in our search and providing a better solution. So therefore, we need to take into consideration these potential directions so that we can come up with a more uniform model that would be more applicable in practice to solve software engineering problems.
So thank you, Mohammed. So another bunch of challenges arise also with the reproducibility, especially that the non-deterministic nature of search-based algorithms represent a real barrier when reproducing the results. So as the output can have slight variations from one execution to another, and this can represent the problem when we try to reproduce the results. Another challenge can be related also to the hyperparameter tuning, as we need to run multiple parameters and see what is the best combination or what is the right hyperparameters values that we need to use for a given problem, and these hyperparameters can differ from one problem to another. Also, another challenge can be related to defining the fitness functions, as we need the clear mathematical function that could be implemented as a fitness function to solve a problem. Also, another problem can be related to the data sets used, especially that sometimes data confidentiality is a concern with several companies, so that we cannot reproduce the results. Instead, we need to have some aggregated data sets, and we cannot reproduce the final results. Also, training can be problematic when it comes to the problem of how the dataset can be split into training and testing dataset. An interesting idea is to take published papers in search-based software engineering and try to write a reproducibility report. And it's interesting also to teach this to new students. For example, in a course project, this could be interesting for students to show them how to write a reproducibility report. And also, it's interesting for research papers on SBSC to have replication packages, so that it will facilitate the replication of and the extension of these works in the future. There are many other challenges when it comes to the automation level. The goal of optimization is to provide automated solutions. However, software engineering is basically a set of human-centered activities, so there should be an interface between automated solutions and software engineering problems to be solved. And one of the interesting ideas is to explore more interactive approaches so that the developer can be involved in designing the solution itself. So we can benefit also from the wisdom of the crowd when designing your solutions instead of keeping them fully automated. As software engineering is evolving rapidly in the last few years, so we may also need to consider more dynamic SBSC adaptations so that the fitness function, for example, can change over time and can be adapted when the context of the software project change. For example, when a new bug is detected, or when a new library becomes deprecated, or even when a developer leaves the development team. So the changes are sometimes unavoidable in most of the time in software projects in practice. So we may need better adaptations to the of the fitness function or of the search space to be adapted to these changes of the environment, especially in software engineering. And in addition to all of these challenges, so we was mainly talking about how can optimization help SBSC. Now at the same time, we may also need to look at how search software engineering can also help with developing AI or optimization enabled software systems. So these all are software systems at the end, and they need software engineering techniques to be evolved. Like for example, we have seen in the case study the MOA framework, which is at the end, this is a software project that is hosted on GitHub, and there are many developers working around, and it's visible to all people. And at the end of the day, this is a software project that needs software engineering techniques. So like any software project, AI and optimization enabled systems such as MOA framework, they need to evolve rapidly. For example, to fix bugs, they can have also code smells, and they need refactoring, they need code review as well, they need project management, continuous integration, development, etc. So this will open up actually a new debate on the relationship or the synergy between artificial intelligence and software engineering in both directions. So which is another story that deserves some more detailed discussion on this topic. So now let us have a roadmap. I will go back to my colleague Mohammed M to have this roadmap.
So let us summarize now. SBSC in a nutshell is about writing a fitness function that will guide an automated search. So to use SBSC and solve a software engineering problem, we mainly need to first identify the right encoding or the representation of the solution. Then we have to look at what properties that we need to capture and we will want to evolve in our solution. And then we have to look at how can we formulate those measurements into a fitness function. Then we have to define how we can evolve our solution to provide the best and the latest ones and potentially solve this problem. So SBSC in general has been applied to solve many problems in almost all software engineering development lifecycle. And if one day you want to do this, so your homework for today would be to take any problem in software engineering, and you can actually SBSC it if you follow the following steps. Okay, and if you do that, if you take this software engineering problem and you SBSC it, you may one day end up having yourself being part of this great community that we have here. So these are all the researchers that I was able to find, in which we were able to find in Google Scholar, that would have the tag of SBSC as their main research or one of their research interests. And I'm sorry if I have missed any of the great people that worked in SBSC. This is just not a non-exhaustive list. So apologies if I'm missing anyone, but this will tell you that this a very great community of diverse people that are been working in solving software engineering problems using search-based algorithms. So this perhaps takes us to the summary of this presentation. So in this presentation, we have looked at what is the definition of search-based software engineering, and then we have looked at how we can apply software engineering to solve multiple problems. Then we have also looked at some hands-on demo on how we can take an existing problem in software engineering and solve it using the M-Wave framework. And finally, we have explored some challenges that we still need to explore in order to improve the maturity of our modeling for this problem. So with that being said, I hope that you have enjoyed this tutorial. Thank you very much. On behalf of me and myself and my colleague Ali, we hope that you have learned something useful, and I hope to see you publishing soon in SPSC. Thank you very much, and enjoy the remaining rest of the conference.